Have you ever wondered how bridges stretch across rivers, how skyscrapers reach for the clouds, or even how the smooth, responsive screen of your smartphone works so flawlessly? These marvels of modern life might seem like products of recent innovation, but their roots go much deeper. The answer to these wonders traces all the way back to the brilliant minds of ancient Greece. The Greeks weren't just content with knowing that things worked. They were driven by a relentless curiosity to understand why and how things worked the way they did. They observed patterns and shapes everywhere, from the symmetry of a seashell to the intricate designs in their mosaics, and from this fascination, the field of geometry was born. For the Greeks, geometry wasn't just about drawing triangles or circles. It was about uncovering the hidden rules and relationships that govern the very structure of our world. Think of legendary figures like Pythagoras and Euclid, names that still echo in classrooms and textbooks today, centuries after they first lived. These pioneering thinkers transformed messy, everyday observations into a logical, organized system of points, lines, and planes, a language for describing reality itself. Their language of geometry became an essential tool for precision in science, engineering, and architecture, allowing us to design and build with confidence. The Greeks insisted on proof, starting with simple, self-evident truths, axioms, and building up, step by step, to complex theorems and discoveries. This logical, stepwise method is the very heart of the scientific method we rely on today, guiding researchers and innovators around the world. Greek geometry wasn't just old math, it was the birth of a new way of thinking, a logical, analytical approach that continues to shape our world in countless ways. Let's journey back in time and discover how these ancient ideas became the very foundation of our technological society, influencing everything from city planning to digital technology. From a simple book of geometric proofs to the complex principles behind GPS navigation, the Greeks' logic and sense of balance remain vital and relevant even in our digital age. Science rules our world, and many of those rules, the very ones we still use today, were first written and explored in ancient Greece. Imagine a book so influential that it's been published in more editions than almost any other, second only to the Bible itself. That book is Euclid's Elements, a work that has shaped the very way we think about logic and mathematics for over 2,000 years. Written around 300 BCE in ancient Alexandria, Euclid gathered, organized, and systematized all the known mathematics of his time into a single, coherent logical framework. He didn't just collect facts, he built a structure for reasoning that would endure for millennia. Elements begins with the simplest building blocks, basic definitions. For example, a point is described as that which has no part, and a line as length without breadth, concepts that seem obvious but are foundational. Next, Euclid introduces 5 postulates and 5 axioms, statements so self-evident that they're accepted without proof. These are the seeds from which all of geometry grows. For instance, one axiom states, things equal to the same thing are equal to each other. It's a simple idea, but it underpins much of logical reasoning. From these humble beginnings, Euclid systematically proved 465 theorems. Each new result was carefully built on the foundation of what came before, creating a logical chain that stretched across the entire field of geometry. He demonstrated, for example, that the angles inside any triangle always add up to 180 degrees, a fact that's still taught in classrooms today. And he gave the first rigorous proof of the Pythagorean theorem, connecting the sides of a right triangle in a way that's become iconic. The Elements showed the world that even the most complex truths could be constructed from simple assumptions, using nothing but pure logic and careful reasoning. This methodical, step-by-step approach became the gold standard for logical thinking, not just in mathematics but in philosophy, science, and beyond. For centuries, Euclid's Elements was the definitive math textbook, studied by generations of thinkers, from Abraham Lincoln, who used it to sharpen his mind, to Isaac Newton, who built his own theories on its logical foundation. Its influence can be seen everywhere, in the way we build arguments, design buildings, and even in the scientific method itself. The structure of logical proof that Euclid pioneered is now woven into the fabric of modern thought. Today, when engineers design bridges or architects draft blueprints, they're applying principles that trace directly back to Euclid's logical system, using geometry to turn ideas into reality. Euclid didn't just give us geometry, he gave us a blueprint for rational thought itself, a way to build knowledge step by step from the ground up. The structure of elements is more than just a book. It's the very foundation of modern science, engineering, and logical reasoning. As Euclid showed, logic is the ultimate tool for understanding, shaping, and transforming our world, one proof at a time. Let's talk about the Pythagorean theorem, one of math's most famous and enduring ideas, a concept that has fascinated thinkers for thousands of years. For any right triangle, a2 plus b2 equals sine c2. It's a simple equation, but its power and elegance have made it a cornerstone of mathematics. Pythagoras and his followers were the first to formally prove this relationship, laying the groundwork for centuries of mathematical discovery. Its beauty lies in its universality. No matter where you are, any right triangle in any context always follows this rule. Builders use it to create perfect right angles. Measure 3 units, then 4, and the diagonal is 5. This practical trick is used on construction sites every day. This clever method has guided the hands of builders and architects for centuries, from ancient temples to modern skyscrapers. The theorem is also at the heart of navigation and mapping. Your GPS uses it to calculate distances, helping you find your way across cities, oceans, and even mountains. It's essential in video games, accident reconstruction, and trigonometry, allowing us to model virtual worlds, solve real-life mysteries, and understand angles and distances. The Pythagorean theorem connects geometry and algebra, revealing the hidden mathematical structure that underpins our world and linking shapes to numbers in a profound way. It lets us measure distances we can't reach directly, whether we're surveying land, mapping rivers, or exploring remote mountain peaks. Every architect, engineer, and pilot relies on this logic, proven over 2,500 years ago, to ensure safety, precision, and innovation in their work. It's geometry in action, shaping our world every day, from the tallest buildings to the fastest planes and even the bridges that connect us. A simple formula with endless real-world impact, reminding us that sometimes the most powerful ideas are also the most beautifully simple. The Greeks didn't just study geometry, they built with it. Their temples are mathematics made solid, designed with harmony, proportion, and order. Symmetry was key. Temples were often perfectly balanced along a central axis. Every element from column height to roof angle was calculated for harmony. The 3 column orders, Doric, Ionic, Corinthian, each followed strict geometric rules. Even subtle details like the curve of a column, entasis, corrected optical illusions. These adjustments made buildings appear strong and stable to the human eye. The Greeks used ropes, straightedges, and compasses, tools of Euclidean geometry, to lay out complex plans. Their mastery of geometry turned abstract math into breathtaking architecture. They showed that geometry wasn't just for scholars, it was a tool for creating beauty and order. Greek architecture is a testament to the power of mathematical thinking. Their buildings inspire architects even today. Geometry was their blueprint for both function and beauty. The Parthenon in Athens is the pinnacle of Greek geometric architecture. Built for Athena, it looks straight and perfect, but it's full of subtle curves and illusions. The stylobate, or base, gently curves upward to appear level to the eye. Columns bulge slightly, entasis, and lean inward, creating a sense of strength. Corner columns are thicker and closer together to correct for visual distortion. The building's proportions may be based on the golden ratio, found throughout nature. Every detail was calculated for harmony and beauty. The Parthenon is a symphony in stone, a testament to mathematics as the language of beauty. Its design shows how geometry can shape perception and create timeless art. The Parthenon remains a model of mathematical precision and aesthetic perfection. Greek geometry didn't vanish, it became the engineer's toolkit for centuries. Roman aqueducts, Renaissance cathedrals, and modern bridges all rely on geometric principles. Builders use geometry to measure, design, and ensure stability. Civil engineering today, bridges, tunnels, skyscrapers, depends on geometry and trigonometry. Blueprints and technical drawings are exercises in Euclidean geometry. Modern tools may be digital, but the logic is ancient. Breaking down structures into geometric components is a Greek legacy. Every modern structure owes a debt to these foundations. Geometry is the invisible scaffolding of our built world. The Greeks' logical tradition still supports everything we build. From Greek temples to computer screens, geometry is everywhere, even in the digital world. Computer graphics build virtual worlds from millions of triangles, polygons manipulated by geometry engines. Calculating perspective, lighting, and movement are all geometric problems. Coordinate geometry, rooted in Greek thought, powers these algorithms. Robotics uses geometry to map spaces, avoid obstacles, and move precisely. Computational geometry designs algorithms for shapes and spaces. Even programming logic, if-then statements, mirrors the logical proofs of Euclid. The Greeks' step-by-step reasoning lives on in software and AI. Geometry is the backbone of digital innovation. Ancient logic powers our modern technology. The quest for understanding shapes and logic continues in every line of code. Greek geometry shapes not just buildings and computers, but all of modern science. Einstein's theory of relativity describes gravity as the geometry of curved spacetime. Chemistry relies on molecular geometry. Shape determines how molecules interact. Biology is full of geometric patterns: DNA's double helix, honeycomb cells, sunflower spirals. Scientists use geometry to model, predict, and understand nature's structures. The Greeks' idea that shape determines properties is true from molecules to galaxies. Geometry is the language for describing relationships in space, physical, mathematical, or cosmic. The Greeks formalized this language, turning it into a tool for scientific discovery. Every physicist, chemist, and biologist uses this ancient logic. Geometry transformed from a tool for measuring land to a system for exploring the universe. The Greek gift of geometry is woven into every scientific breakthrough. From the Parthenon to your smartphone, Greek geometry is everywhere. It's an intellectual foundation we often take for granted. Euclid and Pythagoras gave us more than theorems. They changed how we think. They showed the universe is governed by logical, beautiful rules. Their insistence on proof and proportion shaped centuries of innovation. Geometry's language remains a powerful tool for understanding and designing our world. Learning geometry connects us to a 2,000-year-old tradition of logical thought. These skills are as valuable now as in ancient times. The Greeks' gift of logic and clarity empowers us daily. Every bridge, building, and algorithm echoes their discoveries. The principles of Greek geometry are a living legacy, a timeless echo shaping our modern world.